Dear students, today we shall be discussing about diffraction of light. So, it is the phenomenon of bending of light around the corners or edges of the objects or apertures, due to which light penetrates the geometric shadow of the object. Now, this definition needs a comprehensive understanding. Again, I stated that it is the phenomenon of bending of light around the corners or edges of the objects or apertures, due to which light penetrates the geometric shadow of the object. Now, first of all, let us understand what is the geometric shadow. Imagine you have a light source here, and this is an obstacle. What do you expect to see on the other side? That since the light waves are emitted in all possible directions, we expect to see light here, but not in this region, right? So this region will be called as geometric shadow. Similarly, if you have a light source here and a slit here, what do you expect? You expect to see, and a screen here, for example, that light shall be found in this region and not in this region or in this region. So these regions are again called as geometric shadows. But if the size of this obstacle or this slit is small, how small? Compared to the wavelength of light. If the size of this aperture, this opening, is quite comparable to the wavelength of light, then we see that this light bends and it is also found in the geometric shadow. And this bending of light around the edges, around the corners, is called as diffraction. But the condition is that the size of the obstacle, the size of the opening should be very much comparable to the wavelength of the light, right? Now, this diffraction phenomenon is broadly divided into two categories. One is Fresnel diffraction and another is Fraunhofer diffraction. Fraunhofer diffraction. In Fresnel diffraction, what happens is that the slit is at a finite distance from the screen and from the source of light. The slit is at a finite distance from the screen and from the source of light. And in case of Fraunhofer diffraction, this slit is at an infinite distance from the screen as well as from the source of light. Therefore, what do you need to do here is that you need to introduce collimating lenses or convex lenses to render the path of light parallel and make it fall on the slit, right? Similarly, you need another collimating lens to make the light meet the screen. But here you don't need any convex lenses because the slit is at a finite distance from the source as well as the screen. Now this source can be a point source or it can be a line source. Obviously we can understand that this source of light must be an extended source or a plane source, right? Now what all do you have to study in your course is that you have to find what is the diffraction pattern due to a single slit, due to two slits, due to n number of slits. We shall be doing that in great detail in the subsequent videos. An important example of n slit arrangement is called diffraction grating. So what is diffraction grating? It is an optical device with which we obtain the diffraction pattern, right? Now, how do we construct this kind of an optical device? Suppose you have a plain glass plate, and by means of a fine diamond pointer, you draw some rulings on this glass plate. Obviously, these lines will become opaque, and the rest of the part will be transparent. If the length of or the width of each transparency is A, and the width of each opacity is B, then the sum of the two, that is A plus B, is called the grating element. Grating element. From here I want to take you to the next page. The conditions of diffraction are, that is the condition for principal maxima will be A plus B sine theta is equal to n lambda, where n is the order of the spectrum, right? We shall be doing this diffraction grating, that is diffraction due to n slits, in great detail in the subsequent video, but this is only to introduce you to the various aspects of diffraction phenomenon. Now, if we go by the condition of diffraction, for example, what is the basic equation that governs the principal maxima and minima? It is A sine theta is equal to n lambda, where A is the width of the slit, right? Theta is the angle through which the ray has bent on account of diffraction. Suppose if we expected it to go straight, but it has bent on account of diffraction through a certain angle theta, so this is theta. Now we can write that sine theta for the first order diffraction, that is n equal to 1, is equal to lambda by A, or theta is equal to lambda by A if theta is very small, right? Now let us see what will be the width of the beam, because we know that the width of the light beam is now going to change on account of bending of light. Light is penetrating the geometrical shadow. The width of the beam is going to change. Now let us try to see what is the relation of the width of the beam with the length of the slit, right? Now, how will you do that? Suppose this was the original path of light and it has bent through certain angle, right? So this theta we have already found that it is lambda by A, where A is the width of the slit. Now suppose this light travels certain distance, say Z. What is the width of the beam? Obviously, if this is L, the length of the arc, it is equal to R theta, that is Z theta. So width of the beam is equal to Z theta, or it is equal to Z. For theta you can write lambda by A. But to observe this phenomenon of diffraction, obviously the width of the beam should be greater than the width of the slit. See, if this is the slit and you expect to see light only in this region, but on account of diffraction we say that this light is going to bend. But when will you be able to see that phenomenon strongly, pronouncedly? When the width of the beam will be far greater than the width of the slit, right? The width of this beam should now be quite greater than the width of the slit. Therefore, we say that the width of the beam, for diffraction to be pronounced, to be a pronounced phenomenon that is visible to us, this Z lambda by A should be greater than the width of the slit. Therefore, this Z should be greater or equal to A square by lambda. In fact, this distance We call it as Fresnel distance. Now, for the normal vision of human beings, right, we will try to put the parameters here. For A, we shall replace it by the size of the pupil. The size of the human pupil is 1 millimeter. That is 10 to the power minus 3 meter. And lambda, on an average, the wavelength of light is how much? It is 6 into 10 to the power minus 7 meter. Now let us substitute it here. So ZF comes out to be 10 to the power minus 3. This is a very rough calculation to find when does the phenomenon of diffraction become pronounced to we people, right? So 6 into 10 raised power minus 7. And if you calculate that, it comes out to be 1.67 meter. That means for just a 1 millimeter increase in the width of the beam, the light ray has to travel how much? 1.67 meter. That is why in the day-to-day life, in the common phenomena, we don't observe that frequently the phenomenon of diffraction. Therefore, whenever a doctor prepares eyeglasses for us, they don't take into account the wave nature of light, but they take into account only the phenomenon of ray optics. Ray optics. So, from this example, we are also able to conclude that this ray optics is only a limiting case of wave optics. And why did we say that? Because we did not see that the phenomenon of diffraction is that pronounced, is that visible in our day-to-day examples, right? Therefore, we are mainly dependent on such phenomenon in our day-to-day life in which we treat light as line, as rays. Suppose the phenomenon of reflection and refraction. How do we show them in diagrams? We show them like this. We show them like this, that this is the incident ray and this is the reflected ray. We show them in terms of rays. Similarly, the phenomenon of refraction, we show them in the form of rays or lines, right? Because diffraction is not that pronounced here. Therefore, in the day-to-day examples, it is the ray optics which dominates and not the wave optics. But the broader concept, the broader reality is that light actually has a wave nature and ray optics is only a limiting case of wave optics. In the subsequent videos, we shall be doing some more topics about it.